Okay, so let's continue our look at understanding the tree of life. That is our view of cladistics, this approach to reconstructing the interrelationships of life. So I finished the in-person lecture with this slide. Remember, I had introduced the idea that in cladistics we look for clades, that is complete branches of the tree of life, that is monophyletic groups, an ancestor and all of its descendants. It doesn't matter how transformed. As I said, though, there are many terms that we've used for generations in taxonomy that are paraphyletic, that are an ancestor, but not all the descendants, because people felt they were too transformed. So on this figure, these are two extinct groups of fish. Fish itself is a paraphyletic group. So ostracoderms, which have a bony shell but no jaws, and placoderms, which have jaws but without true teeth, or we discovered actually some of them have teeth. It's a long story. It's outside the scope of this class. And these are both paraphyletic with regard to today's jawed vertebrates, sharks and their kin, and the bony fish, including the land fish, like us. Placoderms are paraphyletic with regard to eunathostomes, to living jawed vertebrates, and placoderms plus eunathostomes, collectively gnathostomata, are paraphyletic, are monophyletic, and this ostracoderms are paraphyletic with regard to them. So we have this baggage of paraphyletic terms in our literature, and we're trying to get rid of them. One way to indicate that you're dealing with a paraphyletic term, when people are conscious of this, is they might use the old name, but not in the formal Latinate form, so like not ostracodermy or placodermy, but in just the vernacular, ostracoderm and placoderm, and put it in quotes, and that tells you it's a non-natural, dubious group. Now, you might think, why is it bad to have paraphyletic groupings? After all, monophyletic groupings are ultimately arbitrary. Not that the monophyletic grouping is arbitrary, they're real because they represent an ancestor and all of its descendants, but our choosing to recognize them is arbitrary. We had to pick an arbitrary ancestor and say all descendants of that ancestor are a member of that group. Well, why not paraphyletic groupings? Well, the problem with that is that they are arbitrary twice. And especially as our knowledge increases, the arbitrariness of our splitting them off becomes more and more apparent. What do I mean by that? So if we were to look at some modern sauropsids, we have turtles and crocodiles here. There's our reptiles in the classic sense. And here is a mourning dove, or rather one of its western kin, in aves, a modern bird. And so reptilia is a paraphyletic group with respect to aves. But where do we draw the line? In the modern world, it makes sense because there's such a morphological gulf, a huge gap in terms of anatomy between the appearance of crocodilians and the appearance of birds. But when we start adding in fossils, we see that there isn't this morphological gulf, this gap. Instead, we see forms that occupy the spots in between. And then we begin to say, well, where did something stop becoming a reptile and start becoming a bird? Is it with toothlessness? Is it with flight? Is it with feathers? Is it with bipedality and warm-bloodedness? We could choose any of them. Instead, the way we approach this now is you never stop being a member of a group. You do start being a member of another subgroup. So nothing stops being a sauropsid if it descends from the common ancestor of all sauropsids. It's just aves is a subset within there. And in fact, each of these nodes is specifying a larger or smaller group within Sauropsida. Now, another set of terminology with groups, and I apologize, I admit this is a very terminologically dense lecture. But if I spread them out as too many dense terminological lectures, then we start missing the meat of the course. That is the actual case studies. So over the years, I've vacillated. Is this one lecture? Is it two lectures? I've tried to cram it down into one. It's actually like one and a third, maybe. But do what I can. So another set of terms: crowns, stems, and total group. So you'll hear this phrase, and I'll use this phrase. You'll be reading it in some of the papers, if you read them where they're using this term, of what's called the crown group. So the crown group is defined as the concestors of the living members of a clade and all of that concestor's descendants. So the dashed line here is present day. The thick lines represent our known fossil record of each of these groups, and the thin lines are the evolutionary relationships here. So the crown group is this group. Now, not all members of the crown group are still alive. For instance, we could talk about, say, crown group mammals. But there are members of the crown group, like, say, a woolly mammoth, which are extinct, or a saber-toothed cat. It's a crown group mammal, but it's extinct. Then there's this thing called the stem group, and that's all taxa that are closer. Remember, closer means shares a more recent common ancestor with, that are closer to the crown group than they are to the next living crown group. So this shares a more recent common ancestor with this guy's than it does with this. I know it looks like there's only one step or two in between, but remember, it's recency of common ancestry. So this is a common ancestor with these guys. This guy shares a common ancestor with the crown group that is not shared with this guy, which is another crown group, because we see it's alive today. So here's the stem group. Now note, stem groups by definition are paraphyletic. They're an ancestor, but not all the descendants. It's the ancestor of everything closer to the crown group than to the next crown group, but it excludes the crown group. So we don't use stem groups as a formal name. We don't give them formal names anymore. We used to. We don't do that anymore. They might be useful, however, as a concept, and we'll definitely see later on where I'll talk about stem members of a lineage and then members of the crown group. Then there's a term, the crown group plus its stem collectively are the total group. Hopefully that made sense. If not, you can ask me about it, or, pause, rewind, and watch it over again. Maybe the second time will help. So here are two living crown groups, well, a representative of each, Crocodilia and Aves. Here are a bunch of stem taxa closer to Crocodilia, and here's a bunch of stem taxa closer to Aves. Okay, so that's some more about groups. Now, how about using cladograms and our character distributions to infer the ancestral states that led as transformations to groups we might be interested in? Because we're certainly going to be interested in that. Now, none of the terminal taxa, none of the tips of the cladogram are likely to represent the ancestral condition for every single one of their states. They're all going to have maybe some of their own autapomorphies, or some combination of autapomorphies and synapomorphies and symplasiomorphies. And that's especially true if we're dealing with things that are all from the same age. So it is true that the duck-billed platypus and the echidna, the two egg-laying mammals today, live today. But not every trait of those two forms is what we would expect in the common ancestor of all mammals, or the common ancestor of, well, in this case, yeah, all mammals. So, in fact, the sort of toothlessness of the duck-billed platypus and the echidna is a derived trait that occurred on the lineage to them. So each terminal taxon potentially has their own specializations evolved after the divergence from the concestor. So we could look to a monotreme, an egg-laying mammal, as an outgroup to the non-egg-laying mammals. And it's useful in many attributes, but not everything in them is actually ancestral. They'll have their own derived traits. However, if we're trying to see the evolution towards a particular lineage, it's the traits along the trunk of the cladogram that are going to be most useful in trying to figure out what an earlier stage in the history of this group was like. By the way, this is Sir Richard Owen. We'll encounter him several other times in this class. Among other things, he named Dinosauria, the dinosaurs. So this is restating what I mentioned before. The ancestral condition, that is what the concestors had, is inferred at the nodes. not at the terminal taxa. Now, what about that information? It's definitely true that fossils are incomplete. After all, we typically don't have their soft tissue. We may not even have all their hard tissue. Most fossils are known from one individual and maybe fewer than one individual, so one incomplete individual. And so we might be limited in our way of inferring the conditions on the cladogram. But sometimes cladograms and the principle of parsimony will help us fill in those gaps. So here we see some of my beloved tyrannosaurs. And we look at, here's the relationships as inferred by a huge phylogenetic analysis. And we're going to look at just one trait, the number of fingers. D long here, an early branch among the tyrannosaurs, retains 3 fingers. Most carnivorous dinosaurs have 3 fingers, equivalent, homologous to our thumb, our pointer, and our middle finger. So Velociraptor and Allosaurus, for instance, they have 3 fingers. Famously, Tyrannosaurus and Gorgosaurus and other derived tyrannosaurs only have 2. They have what we call digit 1 and 2, that is the thumb and the pointer finger. Dryptosaurus we do not have a complete hand for, nor do we have a complete hand for Oleoramus. We know that we have discovered that they fit on the tree in these 2 positions. But we can't actually see their fingers. So how many fingers are there in Oleoramus? We'll start with Oleoramus first. Well, looking at the cladogram, the simplest explanation is that the loss of finger 3, so going from this condition with 3 fingers to two fingers, occurred after the line going to D long branched off from the line going to the concestor of Gorgosaurus and Tyrannosaurus, but before Gorgosaurus and Tyrannosaurus split from each other. Do we know that that's the case? No. We infer that's the case because that's the simplest conclusion. It could be that the ancestor of Gorgosaurus and the ancestor of Tyrannosaurus independently lost their middle finger, the digit 3. But the simplest explanation is that it was lost here. Well, in the case of Oleoramus, it would be a descendant of the taxon that lost the 3rd finger. And so all other things being equal, without positive evidence to tell us otherwise, we infer that Oleoramus only had 2 fingers. Are we absolutely sure? No. But that's the simplest, safest, most parsimonious inference. So, we can use parsimony to figure out. But what about Dryptosaurus? It branches off in the same part of the tree where the digit 3 is lost. Did it branch off after the loss of digit 3 or before? In other words, do we expect it to have 2 fingers or 3 fingers? Well, quite frankly, at the moment, we can't say. We don't have any evidence at present that can help us sort out which side of this transformation it occurred on, it branched off on. So sometimes the answer remains ambiguous, and we have to say, we don't know. And I know this pisses off artists and documentary makers and so forth, because they really they say, well, what do you think Dryptosaurus had, 2 fingers or 3? And I'll say, I don't know. I'm trying to be scientific about it. To the artists, do what looks cool, 3 or 2, but prepare to be wrong. It's in the wrong part of the tree for us to be sure. Now, as a consequence of that, we can infer that the extinct members of a crown group would most likely have all the states that are shared by living crown group members. So, for instance, no, I won't use that instance because we're going to use that instance in a moment coming up. Here's an example. If we were to find a fossil snake, which we've had plenty of fossil snakes, the tongue doesn't preserve. But given that the forked tongue is a common trait within the living members of Serpentes, that's the crown group of snakes, we would infer that extinct snakes within the crown group also had a forked tongue. However, it becomes more ambiguous when we're outside the crown group, because each of these branches are going to share some traits with the crown group, but not all the traits. After all, there are a bunch of traits that evolved after the last member of the stem that we know about split off from the last ancestor of the crown group. So some of the traits that are found in all members of the crown group will be absent in the stem. If those traits are observable in the fossils, great. Like number of fingers. If we have a fossil hand, we can confirm it. But what if it's not found in the fossils? Can we reasonably infer the conditions? Well, there are approaches we can do that. And in fact, there are ways we can describe our level of security, our level of certainty about that. And that's relying on what we call the extant phylogenetic bracket. So extant is the opposite of extinct. And phylogenetic bracket, finding two taxa that bracket, that surround the extinct form that we're asking the question about. The most secure type of inference we call a type 1 inference. And that's where the two members of the extant phylogenetic bracket, where they have the exact same state as each other. So, Ceratomorpha is the clade of tapirs and rhinos. Equus is the living genus of horses. So living horses as well as zebras, donkeys, etc. They're all members of Equus. Eohippus is an extinct form from the Eocene epoch, which is on the lineage that leads to Equus. It shares a more recent common ancestor with Equus than it does with ceratomorphs. Now, ceratomorphs and Equus both have mammary glands. Not a surprise, they're mammals. We don't have the mammary glands preserved in Eohippus. They don't fossilize. But because the presence of mammaries is inferred to have existed in the common ancestor of ceratomorphs and Equus, and indeed all the way down to the ancestor of all mammals, it's an easy type 1 inference to say that Eohippus had mammary glands as well. We haven't seen them. It is theoretically possible they lost them. But without positive evidence that they lost them, it would be foolish to infer that. That would be inferring an evolutionary change for which you have no evidence. The simplest solution is, yes, they had them. Type 1 inference. Now, type 2 inference. One member of the EPB has the derived trait, but the next member of the EPB does not. So, for instance, all members of Mammalia have fur to one degree or another. No members of Sauropsida has fur. They have scales or modified scales that we call feathers. But what about a taxon which shares a more recent common ancestor with mammals than with sauropsids? That is, it is on the stem to Mammalia. Well, we might have some reason to suspect it had fur. For instance, it is a small body size, it shares many anatomical traits with mammals, it probably was warm-blooded and therefore would lose its fur. But without direct evidence, we can't be certain. If we assume it has fur, well, we can suggest it as fur. We might infer it as fur, but that's less secure. It's not as secure as a type 1 inference, because after all, fur could have evolved after the ancestor of Hadrocodium split off from the ancestor of mammals, or before. Those are equally parsimonious. Now, sometimes the fossil record will help. Sometimes we'll find a new taxon that can serve as a member of the EPB even though it's extinct. Maybe it's from a Lagerstätte, remember, a site of spectacular preservation. And so stuff that doesn't normally preserve is preserved. And that's the case here. Castricata is a fossil stem mammal with fur preserved, and it branched off well before the common ancestor of Hadrocodium and Mammalia. So the simplest inference now is that fur evolved before the concestor of Castricata plus Mammalia, and therefore Hadrocodium would have inherited fur, and without any evidence to the contrary, we would have to infer it had fur. Infer it had fur. Sorry about that. Hopefully you saw how that changed it from being a type 2 inference to really being a type 1. Although Castricata is cheating. It's not actually extant, but at least it's got the information. And then there's what we call type 3 inferences. And that's where we infer that the extinct form had a trait that was a different state than either of the two present forms. So neither crocodiles nor birds have muscular cheeks or skin cheeks. There's not much in the way of a cheek. There is the suggestion, no cheeks inferred to be present in the common ancestor of both. There's the suggestion that some types of dinosaurs, of a group called Ornithischia, the bird-hipped dinosaurs, that they might have actually had a cheek-like sheet of skin. Now, there's no phylogenetic support for that. So this is a type 3 inference. It's weak phylogenetically. That doesn't mean it's wrong. That means that our inference of it can't rely on phylogeny. We would have to use other lines of evidence to infer it. So hopefully that helped in seeing how phylogeny can help us figure out the strength of an inference of a fossil trait, or a trait in a fossil. The last thing I'm going to look at here is how we can begin to combine stratigraphic information, so geologic time, and cladograms to determine the minimum divergence time, the last time in history two lineages could have been one. That is, the last moment we would expect there to have been a concestor to those two lineages before it diverged. Now, this minimum divergence time almost assuredly is later than, is closer to us than the real divergence time. But the real divergence time we're unlikely to sample. We're unlikely to be lucky enough to find the rocks where we see that divergence happening as recorded. Maybe we will be lucky sometime, but we're unlikely in most cases. So this gives us a minimum boundary. And this is the way it works. Here we have the ranges of taxa through time. The red bar represents the fossils as known, from their first appearance datum to the last appearance datum, with oldest on the bottom and youngest at the top. And over here is our phylogeny for these same taxa. We can map the phylogeny, the cladogram, I should say, onto the known ranges, accounting for the fact that sometimes the connection requires there to be a branch that we don't see in the fossil record. So let's go over here. We see that E and F are each other's sister taxa. Because they're sister taxa and not one's an ancestor to the other, they descended from a concestor. That concestor had to have occurred before the earliest occurrence, the first appearance datum, that FAD is first appearance datum, of either of the two descendant taxa. In this case, it's the first appearance datum of F. So the last moment in time there could have been a concestor between E and F would have been immediately before the first appearance of F. How much earlier? We don't know. This gives us a minimum. In reality, because we already recognize this as being a member of F from that early on, the real divergence is probably down here somewhere, but we can't tell yet how far down. This gives us a minimum. Now, we did the same over here with A and B, but notice our fossil record for A doesn't go down. It doesn't even go down to the time of B. So we infer what we call a ghost lineage. Ooh, ghost lineage. Okay, a ghost lineage is an extension of the range of the line, in this case leading to A, that's currently unsampled in the fossil record. We infer it existed because of the sister group relationship. And if these are indeed sister taxa and not ancestor and descendant, then there had to be members of the A lineage that existed back here in time when B was around all the way to the point of divergence. Now, there's many reasons why we might not have found that ghost lineage. A might have lived in E-world, or the lineage of A might have lived in E-world. Remember, we don't get fossils in E-world. It might have lived in a region that we simply don't have fossils from. It may be that we've actually found those fossils but don't recognize them as belonging to A. There's lots of reasons, but we can infer this ghost lineage existed. Now over here, B and C both appear in the fossil record at the same time. But given the evolutionary relationship here, we know that the concestor of C plus the AB lineage had to occur earlier than the concestor of A and B, because after all, the concestor of A and B is the descendant of the concestor of AB plus C. And so we don't know how much earlier. We would use the same date, but we would recognize it had to have been earlier. We just can't strongly assert how much earlier. And so with the combination of all this kind of information, anatomical transformations, position in the stratigraphic record, the search for the most parsimonious tree, and so forth, we can begin to reconstruct not merely groupings of organisms, but through that grouping, the story of evolutionary divergence, adaptation, extinction, and flourishing throughout the history of life. And those are the sorts of stories we'll explore later in this course. But before we get to that, next Tuesday's lecture is going to be the biggest picture of all for this course, which is going to be a one-lecture review of the entirety of the history of our planet. Within that will be the evolution of the tree of life. Take care, see you in class, and if you have questions, don't forget to email me. I'll try to answer you. If it's a big enough question, I'll answer everyone the question that you ask. Take care. Bye.